The tires beneath your car contain a chemical almost nobody thinks about. It's called 6-PPD, an additive used to protect rubber from breaking down. But when it reacts with ozone, it creates 6-PPD quinone, a toxic compound linked to mass die-offs of coho salmon after rain washes tire particles into waterways. Regulators are responding, but finding a safe replacement has proven surprisingly difficult. And that means the problem is still riding on every road. Every tire on your car right now is hiding something. Not just rubber, a chemical cocktail of heavy metals, synthetic polymers, and petroleum-derived compounds, including one specific additive called 6-PPD that reacts with ozone in the air to form a byproduct so toxic it kills coho salmon on contact at concentrations as low as 1 microgram per liter. A 2021 study published in Science identified this compound, 6-PPD quinone, as the cause of a mysterious phenomenon that had baffled marine biologists for decades. Entire runs of adult coho salmon returning to urban creeks in the Pacific Northwest were dying before they could spawn. Not from disease, not from predators, from tire dust washing off roads into streams after a rainstorm. The EPA has since launched an agency-wide action plan to address it, and California has begun regulating 6-PPD directly. But here is the part that should stop you. A consortium of 30 tire manufacturers evaluated 60 possible replacement chemicals in 2024 and could not identify a single proven substitute. Every tire on Earth still contains 6-PPD. Every road on Earth is still shedding it. The world produces roughly 3 billion new tires every year. About 800 million become waste annually. The rubber industry consumes around 29 million metric tons of natural and synthetic rubber per year. And for the 5th consecutive year, global natural rubber production has fallen short of consumption. Southeast Asia produces over 90% of the world's natural rubber, a dependency that has already destroyed more than 4 million hectares of tropical rainforest since 1993, an area larger than Switzerland. And now, electric vehicles, which weigh 20 to 30% more than their gasoline equivalents, are wearing through tires up to 30% faster, threatening to accelerate demand even further. There is no escaping rubber. It is in every airplane landing gear, every surgical glove, every gasket sealing your plumbing, every belt driving your engine, every vibration damper in every building over 10 stories tall. A single modern car contains over 200 individual rubber components beyond its tires. A Boeing 747 uses roughly 1 ton of rubber in its tires alone. Tires that must absorb the impact of 250 tons hitting concrete at 150 miles per hour and do it dozens of times before replacement. Rubber is as fundamental to modern infrastructure as steel or concrete. And unlike those materials, it depends almost entirely on a single tropical tree species grown in a narrow band of equatorial territory that the world's largest consumer, China, does not control. So when researchers at one of China's leading agricultural universities announced they had grown military-grade rubber in one of the most inhospitable deserts on the planet, turned a medicinal tree into a strategic industrial crop, and published a breakthrough extraction process that makes large-scale production viable for the first time, the engineering world did not just notice. It recognized a material that could rewrite the geopolitics of an entire supply chain. Now let us get into the full story, because the reason this matters reaches far beyond rubber itself, the invisible dependency. To understand why this discovery shakes the foundations of global industry, you first need to understand just how vulnerable the world's rubber supply actually is. Natural rubber comes from one tree, Hevea brasiliensis. Originally from the Amazon, it was transplanted to Southeast Asia in the late 19th century. And today, Thailand, Indonesia, and Vietnam collectively produce the overwhelming majority of the global supply. More than 90% of global natural rubber production is concentrated in Southeast Asia. That is not diversification. That is a single point of failure for an industry worth tens of billions of dollars. feeding into supply chains worth trillions. And the tree itself is fragile. Hevea requires consistent tropical heat and humidity. It grows only within roughly 10 degrees of the equator. It is susceptible to South American leaf blight, a fungal disease that devastated Brazilian plantations in the 1930s and 1940s, and has never been introduced to Asian plantations. If it ever crosses the ocean, the consequences could be catastrophic. This concentration is not a minor logistical detail. It is a strategic liability that affects every country that manufactures vehicles, aircraft, medical devices, or industrial machinery. China is the most exposed. It consumes more natural rubber than any other nation on Earth, roughly 5.7 million metric tons in 2022 alone. But it produces almost none of it domestically. China's import dependency for rubber sits at approximately 85%. In 2024, the country imported around 6.2 million tons of rubber at a cost exceeding $9 billion. Nearly all of it arrived by sea, through the Strait of Malacca, a channel that in some places is less than 3 kilometers wide. Here is where the story shifts from economics to national security. The Strait of Malacca handles over 60,000 vessels per year, roughly 25% of all global maritime trade. Approximately 80% of China's imported crude oil passes through this single corridor. So does the majority of its rubber. In strategic planning circles, this dependency has a name: the Malacca Dilemma. Coined by President Hu Jintao in 2003, it describes the nightmare scenario in which a foreign naval power, specifically the US 7th Fleet, could blockade or interdict Chinese shipping through the strait during a conflict and strangle the economy without firing a shot. Critical raw materials for Chinese industry, iron ore, copper, energy, and rubber all flow through Malacca. And rubber is not something you can substitute overnight. Every military vehicle needs tires. Every fighter jet needs seals and gaskets. Every submarine needs vibration dampeners. Every rocket motor needs elastomeric insulation. Every armored vehicle needs ballistic-grade run-flat tires. A modern main battle tank can consume an entire set of road wheels and track pads in a single extended deployment. Cut the rubber supply, and you do not just inconvenience an economy, you degrade its capacity to project military force within weeks. China has spent billions building alternative routes for oil and gas, pipelines through Central Asia, the Power of Siberia project with Russia, overland corridors through Pakistan and Myanmar. But rubber does not flow through a pipeline. It is a physical bulk commodity that arrives on container ships. There is no overland workaround at the scale China requires. Either you control your own supply, or you remain dependent on the sea lanes. That vulnerability is why what happened in the Gobi Desert matters so much more than a simple agricultural experiment. The tree that nobody took seriously. Forget the tropical plantations for a moment. In central and southern China, along the Yangtze Plain, there has always been another rubber-producing plant. Eucommia ulmoides, known locally as Duzhong. For centuries, it was valued primarily for its bark, a staple of traditional Chinese medicine prescribed for strengthening bones and lowering blood pressure. Tear a Duzhong leaf in half and you will see something unusual. Thin, stringy latex fibers stretching between the two pieces, visible to the naked eye. Duzhong produces rubber, but not the same kind as the tropical Hevea tree. Hevea rubber is cis-polyisoprene, an elastic and stretchy polymer. Duzhong rubber is trans-polyisoprene, a tougher, more rigid molecular structure. Where conventional rubber excels at flexibility, Duzhong rubber excels at durability, wear resistance, and structural strength. For most of modern history, this distinction made Duzhong a curiosity rather than a contender. The extraction process was difficult and labor-intensive. Yields were modest. Production remained small-scale and concentrated in a few provinces. Nobody seriously considered it as a strategic replacement for imported Hevea rubber. And then two things changed simultaneously. First, geopolitics made domestic rubber production a matter of national survival. Second, a team of scientists figured out how to grow it in a desert. The Gobi experiment. In 2016, Su Yinchuan, the Dean of Forestry at Northwest A&F University in Shanxi Province, did something that most of his colleagues considered reckless. He leased 14 hectares of barren, windswept land in the Gobi Desert in Xinjiang and planted Duzhong trees on it. It was the first time the species had ever been planted in that region. The Gobi is not a place where trees are expected to survive, let alone thrive. Summer temperatures exceed 40 degrees Celsius. Winter drops well below -20. Annual rainfall barely reaches 100 millimeters in some areas. The soil is alkalite and mineral poor. Hevea would not survive a single winter in the Gobi. It needs minimum temperatures above 20 degrees Celsius year-round, annual rainfall exceeding 2,000 millimeters, and rich, well-drained tropical soil. The Gobi offers the opposite of every one of those conditions. Duzhong does not care. It is a deciduous tree that evolved in temperate China. It handles drought once established. It withstands frost that would kill Hevea in days. It grows in hardiness zones stretching from the subtropics to regions with sustained sub-zero winters. What it needed was not a gentler climate. It needed the right genetics and a fundamentally new approach to extraction. Consider what the research team actually had to solve. The first challenge was biological. They built a dedicated breeding base in Luoyang County in Shanxi and systematically screened more than 50 elite Duzhong germplasms collected from across China. Using key performance indicators for both medicinal value and rubber yield, they ran a multi-year breeding program, ultimately producing strains specifically adapted to arid desert conditions while maintaining commercially viable rubber content. The second challenge was chemical. Duzhong stores its rubber differently from Hevea. There is no single tap point. The rubber is distributed across the entire plant. The fruit peel contains 15 to 18% rubber by weight. The bark holds 8 to 10%. Even the leaves contain 2 to 3%. Extracting it required processing the whole plant, and doing that economically required a completely new approach. In November 2025, Professor Zhu Mingchang, who had worked on the project from the start, published a breakthrough: a rubber priority extraction process, published in ACS Sustainable Chemistry and Engineering. The method combines low melting point, environmentally friendly solvents with biological treatment for initial gum separation, followed by targeted steps to isolate the rubber itself. The result is a faster, cleaner process that significantly lowers both energy consumption and solvent use while delivering high yields and exceptional purity. This was not a marginal improvement. Previous extraction methods were slow, energy-intensive, and required harsh chemical solvents that undermined both the economics and the environmental case for using a bio-based rubber in the first place. Zhu's method solved all three problems simultaneously. It was the missing piece that makes large-scale Duzhong rubber production practical for the first time. And because it was published in a peer-reviewed journal, the process is now part of the scientific record, available for replication, verification, and improvement by researchers worldwide. What desert rubber actually does differently? Now stop and ask the obvious question. Why would anyone pay more for desert-grown rubber when cheap imports from Thai plantations are available? The answer is that Duzhong rubber does things conventional rubber cannot. Laboratory testing has shown that adding just 3 to 5% Duzhong rubber to a conventional rubber compound significantly increases durability and wear resistance. Tires last longer. They resist punctures more effectively. For military vehicles operating in extreme conditions, where a blown tire can mean the difference between survival and catastrophe, that performance margin is not a luxury. It is a requirement. But the applications go beyond tires. Duzhong rubber has a unique dual nature. Depending on how it is processed, it can behave as a thermoplastic, a thermoelastic shape memory material, or elastic compound. Researchers have used it as a matrix for electromagnetic interference shielding composites. Published studies show that Eucommia ulmoides gum composites combined with carbon nanotubes achieved electromagnetic shielding effectiveness values exceeding 80 decibels at frequencies between 8.2 and 15.6 gigahertz. That puts it in the performance range used for stealth coatings and radar housings. To understand why that matters, consider what 80 decibels of shielding effectiveness actually means. At that level, more than 99.9999999% of incoming electromagnetic energy is blocked. The material does not just reduce interference, it essentially eliminates it. In military applications, this is the difference between a radar housing that leaks electronic signatures and one that renders a vehicle electronically invisible at certain frequencies. This is where the Chinese military becomes the anchor buyer. Even if desert-grown rubber costs more per kilogram than imported hevea, the People's Liberation Army will pay a premium for a guaranteed domestic supply of a material that enhances tire durability and enables advanced electromagnetic shielding. National security planners put supply chain reliability above cost efficiency. The extra functions as an insurance premium, money spent to eliminate catastrophic supply risk. This is not unusual. Governments routinely subsidize strategic industries. The U.S. Department of Defense underwrites semiconductor research. Nations maintain strategic petroleum reserves at enormous cost. China is doing the same thing with rubber, except it is growing its insurance policy in the desert. The scale that changes the math. Here is where the numbers make the story impossible to ignore. When Su Yinchuan planted those first 14 hectares in 2016, Duzhong was a niche medicinal crop with no serious industrial footprint. Today, China cultivates Duzhong on approximately 300,000 hectares. Under the National Duzhong Industry Development Plan, which runs from 2016 to 2030, the government intends to expand that to 3.3 million hectares by the end of the decade. That includes another 300,000 hectares in Xinjiang alone, carved directly from the Gobi. Pause on that trajectory. From 14 hectares to 300,000 in under a decade, and a target that is more than 10 times larger by 2030. That is not an agricultural experiment. That is an industrial mobilization. At 3.3 million hectares, China would control the world's largest cultivation area for a domestic natural rubber source. Combined with Zhu Mingqiang's new extraction process and the breeding program's desert-adapted strains, the country is positioning itself to become a major producer of a rubber type that no other nation currently produces at scale. The environmental argument that nobody expected. Now look at this from the opposite direction. The conventional rubber industry has caused environmental damage on a scale that most consumers never see. A 2023 study published in Nature used high-resolution satellite mapping to reveal that rubber plantations in Southeast Asia caused at least 2 to 3 times more deforestation than previous estimates suggested. Between 1993 and 2016, an estimated 4.1 million hectares of tropical forest were cleared for rubber, with almost 3/4 of the destruction occurring after 2001. Over 1 million hectares of rubber plantations now sit inside designated key biodiversity areas. Indonesia alone accounts for 46% of the aggregate ecological value lost. The economic benefit generated by rubber cultivation in converted areas, roughly $69 billion, offset only about 1/19 of the ecosystem service losses, which researchers valued at $1.35 trillion. And that is before accounting for what happens after the rubber is used. Tires are a significant source of microplastics. A typical tire consists of 40 to 60% rubber, 20 to 25% carbon black and silica fillers, 12 to 15% petroleum-based extender oils, and a cocktail of vulcanization agents, zinc compounds, thiazoles, and chemical preservatives. As the tread wears, all of those compounds are released as particles onto road surfaces. Rain washes them into storm drains, rivers, and ultimately oceans. The 6-ppd quinone crisis that opened this video is not a one-off. It is the first compound scientists happened to identify. A 2024 review in Science of the Total Environment documented thousands of known and potentially toxic compounds contained in tires. Researchers noted that the environmental problem is persistent and complex, with few effective post-wear solutions. Waste tires are energy-intensive to recycle, and the secondary uses they do find, crumb rubber athletic fields, rubberized asphalt, playground surfaces, continue to release particles and chemical leachates into the surrounding environment. The 6-ppd quinone problem is not an anomaly. It is a symptom of a system that was never designed with end-of-life consequences in mind. Duzhong, grown on marginal desert land unsuitable for agriculture or natural forest, avoids almost all of these problems. It does not displace rainforest. It does not compete with food crops. It rehabilitates barren land rather than destroying productive ecosystems. And because Duzhong rubber is a trans-polyisoprene with green degradability properties, it introduces the possibility, still being researched, of rubber compounds that break down more readily at end of life than the petroleum-reinforced compounds currently used in tires. The race nobody else is running. What makes this story strategically important is not just that China is growing rubber in the desert, it is that nobody else is doing anything comparable. The United States, Europe, Japan, and South Korea all depend on imported natural rubber, primarily from Southeast Asia. None of them have a domestic natural rubber source at any meaningful scale. And the global supply situation is deteriorating. For the 5th consecutive year, natural rubber production has fallen short of consumption. Indonesia, the world's second-largest producer, is losing rubber acreage as farmers switch to more profitable oil palm. Vietnam is seeing similar declines. Thailand's output rose modestly in 2025, but not enough to close the gap. Meanwhile, demand is increasing. The global automotive industry is recovering, and tire manufacturers face a compounding challenge from electric vehicles. EVs are 20 to 30% heavier than comparable gasoline vehicles due to their battery packs. The battery in a Tesla Model S alone weighs roughly 1,200 pounds. The Rivian R1T's battery exceeds 1,800 pounds. That extra mass presses down on 4 small contact patches of rubber at all times. And the instant torque delivery of electric motors means the tires absorb massive rotational forces from the very first millisecond of acceleration. You will not see a burnout, but watch an EV launch hard from a traffic light, and you can see the rubber scrubbing off onto the asphalt. The result is tires that wear out 20 to 30% faster than on comparable gasoline vehicles. Even Michelin has acknowledged this publicly. Bridgestone, Michelin, and Goodyear are all developing EV-specific tires, but the fundamental physics remain. Heavier cars need more rubber, they destroy it faster, and the rubber has to come from somewhere. China's Duzhong strategy does not solve the global rubber shortage on its own. It solves China's rubber shortage. And in doing so, it gives China a degree of material independence that no other major manufacturing economy currently possesses. If tensions in the South China Sea escalate, or if the Strait of Malacca becomes contested, every country that depends on Southeast Asian rubber faces the same vulnerability. The difference is that China, alone among the major consumers, has spent a decade building an alternative. What still has to go right? It is important to be direct about the limitations. Duzhong rubber is trans-polyisoprene, not cis-polyisoprene. It is tougher and more wear-resistant, but it is not a direct substitute for conventional natural rubber in every application. The elasticity profile is different. Applications that require high flexibility, such as surgical gloves, condoms, or elastic bands, still need Havia-derived rubber. Duzhong excels in structural and high-performance applications, tires, gaskets, seals, vibration dampeners, electromagnetic shielding, but it does not replace the full range of products that conventional rubber serves. The extraction process, while dramatically improved, is still more expensive per kilogram than tapping a hevea tree in Thailand. For commercial competitiveness in civilian markets, the cost curve needs to continue declining as production scales. The breeding program has produced desert-adapted strains, but long-term yield stability over decades of harvesting cycles in arid conditions remains to be fully demonstrated. There is also the question of water. The Gobi experiment succeeded in part because Duzhong is drought-tolerant, but drought-tolerant is not the same as drought-proof. Large-scale expansion to 3.3 million hectares in arid regions will require some level of irrigation infrastructure, and water is already a contested resource in northwestern China. The economics of desert cultivation depend on balancing water costs against strategic value, a calculation that makes sense for the military, but may not pencil out for every civilian application. And scale itself is the biggest question. China's current 300,000 hectares of Duzhong cultivation, while impressive, still produces only a fraction of the roughly 14.9 million metric tons of natural rubber the world consumes every year. Even expanding that cultivation to the proposed 3.3 million hectares by 2030 would not make China completely self-sufficient across every rubber application, particularly when you consider the enormous range of products that depend on different grades and properties of natural and synthetic rubber. But complete self-sufficiency may not be the objective. The more strategic goal is resilience. A larger domestic supply could give China a reliable source of rubber-derived materials for priority military, transportation, industrial, and infrastructure applications, reducing its exposure to disruptions in overseas supply chains. In that sense, the value of Duzhong is not simply measured by how many tons it can produce compared with global demand. It is measured by how much critical demand can be insulated from foreign suppliers. And for a country thinking about long-term supply security, that distinction matters. None of these limitations change what the science shows. They define the distance between a proven crop and a transformed global supply chain. What is actually new here? Other countries have experimented with alternative rubber sources. The United States has funded research into guayule, a desert shrub native to the American Southwest that produces a hypoallergenic latex. Bridgestone even operates a guayule processing research center in Arizona. But guayule yields remain low. The plant takes several years to mature, and no commercial-scale tire has been produced from it. The U.S. Department of Agriculture and several European institutions have also explored Russian dandelion, Taraxacum coxsagas, which produces latex in its roots. Pilot plots exist in Ohio and the Netherlands. But extraction is difficult, root biomass per hectare is modest, and the programs remain firmly in the research phase after more than a decade of work. Europe has investigated various bio-based synthetic rubber routes, including conversion of bioethanol to butadiene. All remain pre-commercial. What makes the Duzhong program different is the same combination of factors that rarely line up in one place. A rubber source that grows in desert conditions where no other rubber plant survives, that produces a material with military-grade performance characteristics, tougher and more wear-resistant than conventional rubber, that can be extracted using a published, peer-reviewed process with dramatically improved efficiency and lower environmental impact. That is backed by a national development plan with specific expansion targets and government funding. That is already cultivated on 300,000 hectares with infrastructure in place for 11-fold expansion within 5 years. And that directly addresses a documented strategic vulnerability, an 85% import dependency that the country's military planners have identified as an existential risk. No other alternative rubber program in the world checks all of those boxes simultaneously. The world runs on rubber in ways that most people never think about. It is in the O-rings that seal rocket engines, the mounts that absorb vibration in skyscrapers, the belts that drive factory production lines, and the 3 billion tires produced every single year. The global rubber market was valued at over $40 billion in 2024. and every projection shows demand climbing for decades as vehicle fleets expand across Asia and Africa, and the electrification of transport adds weight and torque to every car on the road. For more than a century, that dependency rested on a single tropical tree species grown in a narrow strip of equatorial territory, a tree that cannot survive outside the tropics, that takes 7 years to reach tapping maturity, and that remains vulnerable to a single fungal disease that has never crossed the ocean but could do so at any time. What happened in the Gobi Desert does not eliminate that dependency overnight, but it proves, for the first time, that it does not have to be permanent. And the country that proved it is the same country that had the most to lose by doing nothing. If you learned something new, make sure to subscribe for more content.